Okay. Let's get started. So last time we learned about the ferromantic field, how the ferromantic field is transformed under Lorentz transformation by using the threefold algebra. So what we did, just let us recap last time. So what we did is just we start with threefold algebra, gamma nu is equal to G mu times, I'm not going to write the 1, but a 4x4 matrix. Starting for threefold algebra, we construct so-called representation as mu, which is the I over 4. That's like this. And from here, so this one will satisfy the Lorentz-Lie algebra as we saw last time. So this becomes a representation of the Lorentz group or Lorentz-Lie algebra, and then we just construct some the field in such a way that the it transforms under Lorentz group like this. So that's how the Dirac field transforms under Lorentz group, and then we check that this action is invariant under the Lorentz transformation. Okay. And then the equation of motion is called Dirac equation, and which is the square root, because if you act, so I'm going to momentum space. It's just okay, and then since it's just dummy index in mu and new dummy indices, we can just do the like this way, which is equal. Like this way. So therefore, Lorentz transformation. So the Dirac equation is the square root, can be understood as a square root of the Klein-Gauss equation. That's what we learned. Okay, today we start learning so-called plane wave equation. So plane wave equation, plane wave solution, plane wave solution. So before that, I would just talk about something called chirality. Chiral means the right-handedness or left-handedness. That's called chirality. To this end, so we just first introduce this kind of matrix. Okay, gamma 0, gamma 1. So we already introduced the threefold algebra, and this gamma matrix we just modify everything. And then one can check that the gamma 5 square is equal to 1. I think this is the exercise. Actually, last time I already gave some answer to the homework too. But anyway, that's easy to show. For instance, minus gamma 0, gamma 1, gamma 2, gamma 3 times gamma 0, gamma 1, gamma 2, gamma 3. And then so bring gamma 0 to here. If you have a minus sign. Do you understand what I mean? So it's an anti-commute. So gamma 0, gamma I is equal to minus gamma I, gamma 0, right? Okay. So therefore, if you bring this one to here and multiply gamma 0 square, you get the 1. So therefore, if you bring this one to here, you get the 3 times minus sign. So therefore, you get the gamma 1, gamma 2, gamma 3, gamma 1, gamma 2, gamma 3. And do the same game. If you bring this one to here, you get the minus sign twice, and the gamma 1 square is equal to minus 1. So therefore, you have minus gamma 2, gamma 3, gamma 2, gamma 3. And bring this one, you have a minus sign, and the gamma 2 square is equal to minus 1. And also gamma 3 square is equal to minus 1. Therefore, this is equal to 1. Do you understand what I mean? So like this. So just do online algebra. It's tedious, but you have to do as a physicist. And similarly, we can just come take the anti-computation relation and gamma 5, gamma mu, and let's do one example in the case. For instance, gamma 0. So let's do the I gamma 0, gamma 1, gamma 2, gamma 3, gamma 0, plus I gamma 0, gamma 0, gamma 1, gamma 2, gamma 3, like this way. And bring this one into here, you get the triple minus sign, so therefore minus 1, and the gamma 0 minus 1. So therefore this will cancel with this one, so therefore this is equal to 0. Do you understand what I mean? Is it okay? Is it okay? If you don't understand what I meant, just tell me. So to bring this gamma 0 to here, you get the minus sign, because you have to commute, like exchange the gamma matrix 3 times. Therefore, minus 1 to the 3 is equal to minus 1 to get this form. Therefore, you get the 0. And you can do the same game. 1, 1, and 1. Okay. So to bring to here, you have to exchange twice. To bring to here, you get the only once. So therefore, you get the minus 1 and the plus 1. So therefore, if they cancel. You understand? So therefore, and then at the end of the day, if you do the computation, you can easily show that the gamma 5. Yep. And then it's the same exercise to do. It's almost obvious. So plug this one into here, and you have to do the same game, and you can show this. And then so we take this basis for gamma matrix last time. And if you use this base, this is equal to, it becomes this equal to minus 1 and 1 by direct calculation. If you take this basis, in this basis, the gamma 5 becomes a diagonal. Minus 1, upper component minus 1, and 1. So then we can introduce so-called projection projection operator, so-called P, I call which is the 1/2 1 plus minus gamma 5. Okay. Is it too small? Should I write it bigger? Can you see from the back? Is it okay? Gamma 5. And then if you use this basis, it's super easy to show that the P plus is equal to 1/2 0, 1, and p minus like this. See?
No help.
No help. Thank you. So like this, eh? So now for you can easily see that the Dirac equation, Dirac field has the 4 component like this way, and if you act this p plus, you get you only just keep like a lower component, and if you act the p minus, you keep the upper component. That's how it acts. Okay. And so we define p plus minus psi like this way. So therefore psi minus is keep like a upper 2 component like this way. And psi plus is lower 2 component. And then Dirac action can be written, so this Dirac action can be written as the S is equal to, if you write down, like this way. Then again, we know the gamma 0 is something like gamma 0 is something like 1, 1, right? In our basis, so therefore it exchange. If you act, exchange the gamma u minus and u plus, and then become like this way. This becomes u plus and u minus, and just take the inner product. And at the end of the day, so what you get is that the like this thing. At the end of the day, so you get this kind of equation. Do you understand? Okay. As you can see, so mass term u plus and u minus couples. Mass term couple plus and minus term. On the other hand, the kinetic term couple only plus and minus and minus. Okay. So therefore, it's the massless case. The upper, if massless case, if there is no mass term, plus and minus do not talk to each other. Okay? Do not talk to each other. Do not talk to each other. So sorry, I should write down minus. So only like a lower component, upper component only talk to each other, not the other way around. Okay. Do you understand what I mean? Okay, so and in particular, so this U plus and U minus is called Wahl spinor. So psi of x, so this guy is called Dirac spinor. For component spinor field is called Dirac spinor. On the other hand, U plus and U minus are called, this two component spinor is called Wahl spinor. And then if n equal to 0 case, you just have the so-called Wahl equation. So this is called Wahl equation. So the equation of motion. Yeah. So U plus and U minus is called the Wahl spinor. And so we introduce so-called holistic operator. I call it holistic operator. So Eij, K, E hat I, E Sj. So S is the same as this guy. What was it? This guy. So we just take the only spatial Jk, and P hat is just a P hat. I is equal to Pi divided by Pi, like this. Okay. It's just a unit component. I think that's not true. Sorry. I think there's no I person. Sorry. Absolute bad. It's just absolute bad. Okay. And then so we already know this. So in spatial component, this guy Sij is just a last time. So we just checked that the Sij, Sjk is something like a I over 2, and then this is equal to like this one. So last time we checked this one. So therefore this is equal to 1/2. So 1/2 P unit vector P sigma and divided by this. Okay. So that's what we have. Okay. So that's the and then if you assume the plane wave equation, as I mentioned, plane wave is something like a P plus minus x. It's just a U plus minus P, E to minus I, P dot x. Okay. And then you plug that one into here, and you can easily see that the this one is transformed as the holistic operator acts on the U plus minus of P is equal to plus minus sorry, I just got confused. Plus minus 1/2 P plus minus. So So this one we will see in the I will explain why this should be plus minus the case. It should be the plus minus in here. Yeah, so I will explain how the SH H acts on this U plus minus B on the so I think I shouldn't write down. So from now on, so we just assume this plane wave equation, and then we'll see the how this helicity operator. So this is called helicity operator. So this guy is called helicity operator. Acts on this is plane wave equation, plane wave solution. So that's what we are going to see. Any question at this moment?
Is there sum over P?
Sum over P. Where is sum over?
There's no sum over P.
Here?
Yeah.
There's no sum over P. Okay. Okay, so then we assume that the x dependence is just the plane wave means that the u of p. This is now for component. It's not Wildspinner. E3 minus I p dot x. Like this way, and plug up the Dirac equation. What you get is that the minus m p dot sigma bar and minus m. UP acts on. Do you see that? Can you see that? Okay. Do you see? So this is Dirac equation. So gamma mu is this one. So therefore, of course you know this sigma mu. I hope you understand that sigma mu is equal to 1 to sigma I, and sigma bar mu is 1 minus sigma I. Okay, so that's the 4-component, I would say, power matrix. And then, since the Dirac equation, oh, sorry. Oh, by the way, do you know this notation? Partial slash? Oh, you don't know? Okay. So this is the gamma mu partial mu. So every time, so this p slash means that the this one is also gamma mu. It's a contraction with the gamma matrix. That's called p slash. Okay. It's called slash. And this one's introduced by Feynman. So this notation is introduced by Feynman. So this is gamma mu and partial mu. Partial mu acts on this plane wave and brings the minus I times b, and you get this off diagonal term, and then diagonal part is coming from this here. Okay, do you understand? So essentially, the hidden I times 4 is hidden here. Okay. Okay, so let's construct the solution to this equation. And it's super easy. So it's super easy to construct this equation. So for instance, if you set UP is equal to M times U1, and then P dot sigma bar times U1, this solution is satisfied. This equation is satisfied. Can you see that? So lower component is super easy. So MU1 acts on this one, and then P sigma bar acts on this one, they cancel. That's super easy. And the upper component is you have to use the following equation. So you get the minus m squared, and then P sigma, P dot sigma times P sigma bar. Well, what's that? So what we need to do in the following exercise. say starting x by p sigma times p sigma bar. Okay. So then, so we know I already erased. Okay. So we need to substitute this guy. Okay. And this is equal to p0 square from first component, and then pi and pj times sigma I and sigma j. Okay. Do you understand what I'm doing here? Because I mean, p of course there is a cross term like a p0 1 times pi and sigma I, like this way. Oh, I think anyway, whichever. So this one cancel with the I think minus sign, cancel with p0 1 and then pi and sigma I, right? So 0 and I will cancel each other because of this sign difference. Do you understand what I mean? Is it okay? If you don't understand, just tell me. So what we need to do is 0 square and then the cross term of special component. Is it okay? Do you guys understand? And so this one, so we already know sigma I, sigma j is equal to 2 delta ij. Do you understand this thing? Is it okay? Can you check? It's a small version of critical algebra. Seems like you guys do not. Okay, so sigma 0 is equal to, you can check 1, 1, right? Sigma 1, sorry, not sigma 0, sigma 1. Sigma 2 is equal to I, and which one is minus sign? Sorry. This one?
Yes.
And then sigma 1 times sigma 2 is something like on the other hand, I guess. So therefore, if you add them up, you get 0. But if you multiply them together, you get 1, right? You get 1. So therefore, this kind of critical, small version of critical algebra is satisfied. So therefore, you have to, and this is equal to, so this is equal to 1/2. So therefore, this is equal to p0 squared minus pi squared. Okay? And so therefore, this is equal to m squared. And what we are checking that if this one acts on upper two component, you get a minus m squared. And we know p dot sigma times p dot bar sigma is equal to m squared. Okay? So therefore, they cancel. Is it okay? I hope it's okay to you guys. So therefore, we know this is the solution to Dirac equation, and we just slightly massage this equation in a bit more how to say, in nicer way. Writing mu1 like this way, then up is equal to p dot sigma times c, and then here. Oh, sorry. Is it okay? And we know that the P sigma, P dot sigma and P dot bar sigma is equal to N. So this can be written as P dot sigma C You understand? So n squared, so the P dot sigma and the P dot bar sigma is n squared. So just, do you understand what I'm doing here? So starting from here, I just set NU1 is equal to this quantity, P dot sigma squared C. Okay. And just plug that into here, you get this one. Okay. So, and M is the square root of this quantity, and then so we know that this one cancel, this one is cancel this one, and then this one will cancel square root. So therefore, what we get is that the P dot sigma, P dot bar sigma C and C. Okay, that's actually. And C is just two components. So it just encodes a spin up or spin down. Okay. And then similarly, so this is positive. So we call it, this one is the positive frequency. And you can also consider negative frequency. It's a good exercise to do for you guys. So this is equal. So this is negative frequency. So this is positive. And you can show that do the same exercise. Plug that one into here. Essentially, you get the minus sign here. Okay. Essentially, minus sign here. So therefore, what we need to do is that essentially you need to put the minus sign here. Okay. For B. Okay. Minus sign here. And then coming to here, so okay, and minus sign here, okay, and then minus sign here, So therefore, B of B is equal to I call it A for B. Ader for negative frequency. Ader. So therefore P sigma, P dot sigma bar minus Ader A. Do you agree with me? Is it okay? And Ader is essentially just spin up and spin down. So either whatever, Ader 1, Ader 2, like this, two components here. Can be understood. Any question at this moment? Okay, now we consider plane wave equation as the following. So the Dirac fermionic field takes the following state momentum P. So this is time, energy, and then momentum only takes third component. Okay, z xz. Okay. And of course, the E square minus P square is equal to M square. So So we take this, it's satisfied, so since it's a current. The Dirac equation essentially means should satisfy. Okay, again, it's getting noisy. Okay, so then plug this one into the okay, U of P is P dot sigma and P dot bar sigma and MC, and plug that one into here. And what we get is that the okay, if the C as I mentioned is a two-component sphere, and if C is the up, we will see the following. So we will see the following. So C is equal to 1, 0. If this is the case, so U of P is equal to, and we just assume this one. So essentially we only look at the sigma 0 and the sigma 3. And sigma 0 is just 1, and sigma 3 is 1 minus 1. Okay. Or 1, like this way. And if it is spin up, we just only see the upper one. And be careful about the sign of G mu nu. It becomes E minus P3. I think I should write down P3, sorry. P3, or whichever. P3. Square root of 1, 0. E plus P3, and then 1, 0. Okay, you be careful about sign about the sigma bar, and also this dot means contraction with G mu nu. Okay. Yes.
Square root on E dot sigma means that we diagonalize the matrix and square root the eigenvalue. That means how can we square root the matrix?
How can we square root the matrix? That's a good question. Yeah, I mean, as I like this way. I mean, if you take this the P's third component, of course you can always do the Lorentz transformation. You can take this one, right, without loss of the generality. The momentum is P3. Then always you can diagonalize like this way. So that's what it means. Okay, so then, and if you take mass goes to 0 limit, m goes to 0 limit, so this becomes 0. This becomes, so therefore E becomes P3. So therefore this becomes 0, 0, 1, 0. Okay, and then if you take, say, C, then the opposite sign, yeah, actually it's some number here. And if you take the m goes to 0 limit, some number times number is not important now, 0, 0. Okay, so that's what happened. Okay, that's what's going to happen. And then, so we just look at the helicity operator. Here, helicity operator acts on here. Essentially, helicity operator acts on this one. Will give you acts on this solution UP. Essentially, what we get is that the positive. So therefore, this is last one half UP. On the other hand, in here, H acts on UP is minus 1/2 UP. Okay. Do you understand? If massless case. Okay. Do you understand what I mean? So here, helicity operator 1/2, and P, if it is the upper component, so essentially what we are interested in P3 dot sigma 3. If it is upper component, you just get the plus sign. If it is lower component, you get the minus sign. Okay? Do you understand what I mean? So therefore, so here it's upper component, right? So you have a C and the upper component will give you plus sign, and then if it is lower component, 0, 1 is lower component, and then you get a minus sign. Do you agree? Is it okay? So therefore, so this means that this massless case, you just go to the frame of reference of piece. Let's see. This is P3 direction. Okay. Upper component is right-handed. Upper component, and so this spin up is the right chirality. Okay. So it's along the P3 direction. Okay. On the other hand, C is the 0, 1 is down spinner. Okay, down spinner. It's opposite direction of P3, and then this is the it's called the left-handed spinner. Okay. Do you understand what I mean? It's left-handed. It's left-handed spinner in P3 direction. Therefore, this is the right-handed. Chirality, and this is called left-handed. The chirality. So it's called chiral. Chiral means right-handed or left-handed. So P3 is the momentum of the particle, fermionic particle, and then whether you have a spin up or spin down along the direction of the momentum is called chirality, right-handedness or left-handedness. If in the case of massless case, okay. But if the fermion has a mass, you can always change the direction of the momentum, because I mean, if you do the Lorentz boost, and then of course the particle, the speed of particle is less than the speed of light. Therefore, if you move fast enough, you can just change the direction of momentum. Okay. Do you understand what I mean? Okay. If the particle is just somebody moving slow speed, you can just catch up him and just go go over him, right? So therefore, you can change the direction of P3 so that this chirality that is not Lorentz invariant chirality. Do you understand what I meant? Is it okay? Any question at this moment? If not, I will move on. Is it too fast for you guys? is it right speed or is it too slow? Just tell me. Or is it clear or unclear? Just tell me. Okay. So the last time I told you that the this one is Lorentz invariant spin bilinear. It's called spin bilinear. The bilinear means the you have a two bi means two spinor component. On the other hand, this is not Lorentz invariant. Okay? This is Lorentz invariant. This is not Lorentz invariant. That's I already showed last time. If you already forgot about it, you should watch the last time's video. I think I explained very detailed. And we can just see this one is not Lorentz invariant in the following way. So suppose so we have the so UR P and US. So you can just see by product bilinear. Do you understand what I mean? So we know that the UP satisfies this four component sphere. They satisfy the Dirac equation as a plane wave. Okay, that's we already know. And then UR. So UR is this four component. How to say? Like the okay, and you just multiply like this way. R. Okay. U1P star. I should explain in detail. This R means the U2P star. You understand what I meant, right? P. So this is this guy. Okay. And then you multiply the U1P dot U14P, and you make a matrix. 4x4 matrix. Okay. Do you understand what I meant? So U1 star, U1 star, U2. I think all of it. U2 star, U1, U3 star, U1, U4 star, U1, whatever. You understand what I meant? U1 star, U2. It's just multiplication of the raw vector and raw vector and column vector. You create a 4x4 matrix. That's what I'm doing. Is it okay? I'm sorry. Oh, okay. The swapping. Okay, that's fine. It's maybe I should write this one into here. So that's what I'm going to do. And that one is super easy to do. So then what I need to do is the following. So here you have the P sigma C. And then sorry, am I doing correctly? Sorry. No, I think this is not what I'm doing. Sorry. I'm very sorry. What I explained is totally wrong. Sorry. I'm very sorry. It's just matrix the multiplication of row and column vector. Sorry. You just multiply like this way. Sorry. That's fine. Sorry. So I'm not going to create a 4x4 matrix. So you just multiply like this way. So this is equal to CR P of sigma CR better P dot sigma CR CS, and then P dot sigma bar. Oh, sorry. I think I should write down more precisely. CR. Sorry. Sorry, my brain's not working properly. So like this way. Okay. Do you agree with that? Okay. And we know this sigma bar only differs the sign of a special component. So this one is equal to 2p0. Okay, so and then so this is 2 by 2 not 2 by 2 two component spinner, and you can just contract them, and then this will give you the delta R. So as you can see, at the end of the day, you get the 2 times P0, and this is not Lorentz invariant. P0 can be changed if you do the Lorentz list, right? Okay. So therefore, this is not the Lorentz invariant quantity. Sorry, somehow my brain is not working properly. And then U bar, if you consider U bar, R, P, and US, P, and this is essentially what we have is the CR, dagger, square root, CR, P dot sigma bar. And then you have to use the gamma zero matrix, which is off diagonal 1, 1. And then P dot sigma, P dot sigma bar, C, C, S. Okay. And then now, so we have what we have is CR. Essentially what we have is this one. Okay. So now so this off diagonal 1, 1 swap the P sigma and the P sigma bar. Okay. And then the multiply them together, you get this combination P dot sigma and P dot sigma bar. And we know this one is equal to m squared. And if you take square root, you get the, and so therefore this is equal to, and n is Lorentz invariant quantity. Okay. So therefore this is the Lorentz invariant. So similar calculation will tell you the following. The summary is the like this way. Same calculation, and then what you get is this one. Okay, so that's what you get. You can do the same calculation of B component. And you can get the sense. This. You can get this. So B, there is a minus sign here. That minus sign will give you this minus sign here. Anyway, that you can check by yourself. I'm not going to do that. And then this is the homework. I think actually I give a lot of hint to the homework too. I think, but you can do the same thing by just the sum of the polarization vector, spin polarization vector, SE. So this is the 4x4 matrix. Sorry. So this one will give you, in fact, P slash. So this is homework. So I'm not going to show it to you. But you have to do a very similar calculation. And you have to be careful about how you perform. Okay. So this is the homework. Homework 2. So you have to show this. And this combination will appear when you combination will appear when you do the Feynman problem. Feynman diagonal computation for directives. So you have to use this kind of combination a lot later. Okay. Any question at this moment? It's a bit early, but I think it's a good place to stop and then take a break before going to canonical quantization. So let's take 10 minutes break. So if you submit the homework by hand, you should pick your homework from here. Homework is here. And I should.
What does RNS here?
The spinner, so is the CS. So this is delta R, which means that the CR can have one 2 by 2 component. So when R is equal to 1, it's just 1, 0. And then S is 1, and this is equal to 1. So when S is equal to 2, yeah, it's 2 components.
I have a question about this D-Rock quantum. So we have something that gamma 5 commits with. So also gamma 5 will commit. can we construct a Lagrange like this? So why can't be our Lagrange? So it should be yours in there.
Yes, that's fine.
So the Dirac equation actually is this equivalent to the original?
But that will give you some physically nonsense solutions.
So
Because I mean here, what you get is the term which is minus f plus u minus f plus u plus and u minus. That is fine from
so there will be the energy.
It's a Lorentz environment, but I mean here you need to it's a mass time. Essentially but the time will give you some
Okay, thank you.
yeah, it doesn't make sense. So please, if you submit the homework, please pick by hand. Please pick from here. Pick it from here. And if you have friends which is not present here, absent here, please pick the friend solution too. If you have a friend. Otherwise, I have to pick, bring it back to my office again. So please pick your friend's solution. Homework too. Is this the one you mentioned? Some people are talking to each other.
Yeah.
Okay. Okay. I post solution 1 to the e-learning. So hopefully. Then let me put it now. Stupid. Okay. So one correction. Okay. It's a bit too early to start. Anyway. Should I restart and resume? Yeah, rest. Okay. Okay. So I missed the factor 1/2 here, and I changed selection of now. So factor 1/2. I missed 1/2 here, and in the blackboard I didn't include 1/2 here. Sorry. So the 1/2 should be here to get the correct factor. And also I think p hat j should be pj, sorry, pj, and then this one, sorry, I think I need to include this vector, not formal method, sorry. You need to normalize the only spatial lines. So it's in the previous case I just write them like this way only, but only you need to include the spatial absolute value of the spatial momentum. So this is helicity operator. Okay. Yeah, I think that's okay. Okay, so so I just give solution 1 to the e-learning. So just now, so you can find it in the e-learning. And if you have a question about the homework, you can ask even office work hour or whatever. WeChat, whenever I'll take a look at WeChat. I'm not sure if I can answer immediately, but if you have a question about the homework, just tell me. And then okay. So thanks, Shuton, about this correction. And if you find some mistake in my lecture, just please point it out. It's recorded, so if something wrong, I'm just publicly saying something wrong. So, so please correct me. Thanks, Shuton, for this correction. And then one student mentioned that while I'm giving a talk, you have to be silent. Okay. Anyway, so I don't think you guys are so loud, but anyway, so people should. Anyway, I mean, if you want to talk with a friend to ask, it's also fine. But be careful about the noise, whatever. That's what the one student mentioned. Okay. Anyway, so let's quantize Dirac field. So far, any question? Okay, so then we quantize. So we construct parametric actions, and then it is like a scalar field. We would like to quantize it. So treating the psi as an operator. So the Dirac action is the psi bar of x I slash n. And then we treat this psi bar x as an operator, and then we quantize by canonical quantization. That's what we are going to do. It's very same, almost analogous to the Klein-Gordon case. Klein-Gordon case, we have on half. Like this way, and we treat phi as an operator, and we did we impose the following commutation relation in Heisenberg picture. So we impose deltas 3. Sorry. So we impose this canonical computation relation and then do the Fourier transformation for phi field, and the mode treated as operator. Okay, so that's what we did in the scalar theory, and then we are going to do the very similar thing to ferromagnetic field. Okay, that's what we are going to do. So that we quantize the ferromagnetic fields. From now. Do the same, very similar thing, but yeah, and then this will give you, so essentially what we did is that the phi as the, I forgot. So just to recap what we did last time, p of x. I'm not sure, is this sign correct? I hope so. Like this way, and then we, if you impose this canonical computation relation, what we found is that there's something like Q. Computation relation is very similar to I think I times Q, P minus Q, like this way. I think sign, I may be wrong about sign, plus minus, plus minus. I don't know which one is correct. I don't remember. Anyways, you know, but I don't know. Anyway, so that's what we did. We're going to do the same, very similar thing. And then the free theory, the goal is first to obtain the Feynman propagator. Okay? Feynman propagator. And we want to get the Feynman propagator. Okay, so we treat psi. So as I mentioned, this is a complex field. So this is complex four component. Yeah, spinor field. Complex spinor field. Okay, so now for psi and psi bar, we should treat as a differently of a different operator. As you did in homework. And then, oh, sorry. I didn't include current. And then now we have the S. S here is the spin polarization. It's S is the four component spin polarization. So therefore, what we have is a PS USP. This is a plane wave equation. Essentially, this part is the same as the plane wave equation we considered around here. Okay, but we have a Fourier moment. Okay, and plus BP S dagger. Take the following Fourier transformation, and then so as you did in homework, it's a complex. If it is complex field, you need two modes, A and B. Okay? That's what you did in homework. That's why. So you have to do the homework very seriously to understand the content of the lecture. Yep, so that's the Fourier transformation. And then as in the scalar theory, so we want to treat this B and A dagger, B dagger and A dagger as a creation operator, and then A and B as an annihilation operator. That's what we want to do. But you have to be careful about in the case of permanence, you have to, there is a so-called Pauli exclusion, principle. So Pauli exclusion principle tells us that you cannot take the fermion cannot take the same state. Two fermion cannot take the same state. So therefore, we have to impose the following. So if you have a vacuum and act on a creation operator twice, the same creation operator, maybe I should include the also S here. You have to get 0, because otherwise it violates the Pauli exclusion theorem principle. Okay. That's the same thing here. BPS dagger, acts on vacuum should be 0. This can be only achieved. So if it is the the bosonic case, this is totally fine. This is no longer 0. So how you can act the creation operator however many times you want. Okay? However, for fermion you cannot do that. So therefore, spin statics theorem will tell you that so we cannot take the same statics as the bosons in the case of fermion. So this only can be achieved if you impose something like the AP dagger. So this means that the AP dagger So we want to impose something like this. Anti-computation relation S and T is equal to something like delta P minus Q, and then delta Ts like this way times I, something like this one. Okay. So okay. I think. Okay. I here. Sorry. Okay. So that's what you meant. So here I think 2 pi q. Okay. So instead of sorry, there's no dagger. Sorry. I'm very sorry. My brain is not working. Sorry. I think this can be only achieved by solving font. Yeah, it's so different. So if you impose something like AP S dagger, AQ T dagger is equal to 0. Okay? So for any creation operator, this is achieved. Do you understand what I meant? So if you impose anti-computation relation instead of computation relation, this is achieved. As you can easily see, so APS dagger, if APS dagger plus APS dagger, APS dagger is equal to 0. Okay? If you impose this anti-computation relation. Okay? Do you understand what I meant? So therefore, this should be equal to minus of this one. Okay? This is equal to minus itself. Okay? Therefore, it should be 0. Do you understand? So therefore, for fermions, what we need to impose is anti-computation relation instead of computation relation for canonical quantization. Okay? Due to Pauli exclusion theorem. So that's what physics tells us, that's what nature tells us, and then let's impose the anti-computation relation for canonical quantization. Okay. So therefore, canonical commutation relation, commutation relation for Dirac field should be found psi A of x Tx. So I just directly go to the Heisenberg picture. Sorry, so I should include this one. Is equal to delta Does Pesky and Schroeder include I here? Sorry, can you check now? My lecture notes, I was not careful about it. Can you check now? Okay, so we impose this one up to some coefficient. Did you check? No I. Okay, thank you very much. Okay, so that's what we are going to impose. And then, in fact, let's plug this do the Fourier transformation, and then you can get the following thing. You can just from here, it's good exercise to do. So Fourier transformation. I don't think. Yeah, it's a good. I don't think it's a good idea to perform this. It's equal to sorry, R and S. Better. Is equal to this and other commute, other anti-commute, sorry, other anti-commute. Creation operator itself and annihilation operator itself, anti-commutes. Like this way. And then, so that's equivalent. So if you just do the Fourier transformation over here, and then do the impose this canonical anti-canonical commutation relation, we get this. This is good exercise, and I don't think it's illuminating to perform here. So most likely I would make a mistake. So before going up, I mean, I forgot to explain the very, very important thing. Sorry. Of course, you have to find. So the reason why we take sine dagger is that this is canonical conjugate of this one. So recall that the Dirac equation. Do I have Dirac equation here? Okay, good. So Lagrangian delta psi dot, okay, to find a canonical conjugate momentum, okay. Do you understand? So first here. So when you impose canonical commutation relation, you impose psi and its canonical conjugate momentum, right? So first you have to find, and we know this one we treat it's equal to psi dot in fact. But anyway, so here if you look at Lagrangian, so Lagrangian this is Lagrangian, and then gamma 0 psi 0 appear like this combination, and so that the psi dot only appear here, okay, this term, okay, and then psi bar is gamma 0, gamma dagger, psi dagger gamma 0, right? Okay. So therefore, if you take the variation with respect to psi dot, what you get is the psi dagger gamma 0 times gamma 0, but gamma 0 squared is equal to 1. So therefore, what you get is this is equal to psi bar. Okay. And so therefore, from Dirac theory, the canonical conjugate of psi is indeed psi dagger. Therefore, you impose this canonical commutation relation between coordinate and momentum, essentially. Okay? But here, instead of the commutation relation, you impose anti-commutation relation due to the Pauli's exclusion. I mean, that's the spin statics theorem. Okay. think this is a very good exercise, so you guys should do it by yourself. Any question at this moment? Yeah, if I try to do it now, I think most likely I'm just wasting time with you guys. Okay, so that's the case. So it's like an exercise for you guys. This is exercise. Okay, and then so let's construct Hamiltonian. I forgot. Okay, Hamiltonian density is pi times psi dot minus Lagrangian, and we know pi is equal to psi dagger, and phi dot minus Lagrangian, and we know that the this is equal to psi dagger phi dot minus. I hope I'm not going to make a mistake. I'm very sorry. Oh, that's why I see. I missed the important fact that here I should have an I here. Here I should have an I here. Is it correct? Yeah. Sorry. Sorry, I missed this I. Here there's the I here. So therefore, in fact, more precisely speaking, you need to impose like this way. Do you understand what I mean? This is really canonical conjugate momentum, and you need to put the I here. That's why I was asking why is there no I here. Anyway, so therefore this is I times here, and then I times here, and then this is psi dagger phi dot, and then so I just decompose the Lagrangian part is the time derivative and the spatial derivative. Okay. Spatial derivative. Then of course time derivative cancel, and what you end up is the psi bar times minus psi bar I times gamma I plus m psi bar and psi. Is that okay? Sorry, and I need to put up psi here. You understand? So this is a Hamiltonian density, and the Hamiltonian can be obtained by just spatial integral of this Hamiltonian density. So therefore, this is equal to this is the Hamiltonian. Okay, and then we're just going to plug this one into here. Plug this one into here. And then what you end up with the, I think, I'm not sure. Yeah, plug that into here, and what you end up with, this is also a good exercise to do. what you end up with the following. So the plug into here, dqp 2 pi of q. And then it's very similar calculation as you did in the scalar theory. Sum over s, ap, dagger, ap, s, and then plus sorry. Yeah, so here, in fact, you get the minus BP, S, and BP, dagger, S dagger, in fact. That's what you get. This is a good exercise to do, but I'm not going to do in this lecture. It's going to just a Fourier transformation and do that plug it in, so I'm not going to do that. And then, so it's here, I have a very, the same problem will appear for as the scalar theory, but here you have to be careful about sign. So if you take normal ordering, as I mentioned, normal ordering, so you have to put the creation operator to the left and annihilation operator to the right. Okay? Annihilation operator to the right. If you do that, this one is indeed equal to dpq 2 pi of q EP sum over s APS dagger APS plus BP S and BP dagger BP S minus 2 pi cube delta cube V. So here, there's a minus sign here. It used to be plus sign. Okay, that it used to be means in scalar theory it was plus sign. It was plus sign, but permanent theory you have the negative sign. Okay. So therefore, if you have plus scalar theory, scalar boson and fermion, this infinite energy will cancel each other, in fact. Do you understand what I mean? So this is really happening in so-called anyway, so supersymmetry. I mean, as you may heard of it, so supersymmetry is the symmetry between boson and fermions. So you have to have the scalar field and the fermionic field, and then suddenly some symmetry will show up. Suddenly, if you have a free scalar, free fermion, suddenly there's a symmetry that exchange boson and fermion will show up, and then somehow they can this vacuum energy, infinite vacuum energy, cancel each other. That's that appears. But in any case, if you have only fermion, you can treat as a scalar theory. This one is just the artifact of the infinite volume. With the infinite volume, and just ignore, and you have this Hamiltonian. Okay, so this can be understood. The infinite term can be understood as artifact of the infinite body, and the sign is just because of the opposite is spin statics from the bosons. Okay, so that's what's really happening here. So this exercise part, the reason why I give it to exercise is because I didn't bring the note for this calculation, so most likely I will make a mistake if I do it now. So I just don't want to waste your time for making a mistake. If you want to know, I can give you some note for explicit calculation later. Okay, for this, I mean, essentially you have to do very tedious Fourier transformation calculation, unfortunately. That's what we need to do for this kind of free quantization. Okay. So then, even though, so now, so we have the Hamiltonian can be written like this way. So essentially, H, so normal ordering is essentially what you get is the QP 2 pi of Q P S AP S dagger plus BP S dagger BP S. Okay. So that's normal ordering, and you just forget about this normal ordering constant for infinity. And then here you have the, so even though this operator is the, you need to impose computation relation like here, but however, if you just consider the computation relation between operator itself, you have to consider computation relation. So here it's A and B are Fermat operator. Okay, Fermat operator. However, if you have two Fermat operator, it becomes bosonic operator. Okay? It becomes bosonic operator. So therefore, you have to impose the computation relation between. Actually, it's not imposed, but it's natural to consider the computation relation between here. Okay. Maybe I should write down the maybe. So P and Q. I should call Q. So then, what you get is that the so let's do the computation. So if you impose AQ, okay, AQ. So from the left, and then on the other hand, so this one is equal to HAQ minus AQ. Oh, sorry, I think I should put some I call R like this way. And on one hand, you put the AQR here. On the other hand, you put the AQR here, R here, and then take the computation relation. But first, you have to swap these two operators. You get the negative sign, okay, and then you have to take the okay. So therefore, this sign issue. So it's very natural to take the computation relation, because first you have to bring this one into the, you have to exchange this one and compare with this the other one. Do you understand what I mean? Okay, let's do that. So AQ, this is sorry, APS, APS, AQR. So the important part is this part, and then minus AQ R AP S dagger. Okay, and this is equal to so first you have to swap which one? So you have to swap these guys. So you have a minus AP S dagger and the AQR APS. And a minus AQR, APS dagger, and APS. And so therefore this is equal to minus APS dagger, AQR, and then APS. Do you agree? Is that okay? So then you just impose this Fourier transform anti-computation relation, you get the 2 pi. Q delta. Like this way. Okay? And plug that one into here, what you get is that the minus EQ. Sorry, I think I should put delta RS. Okay. Do you understand what I mean? Are you following? Similar thing, you have to do this, so you can do the same thing for a dagger. EP, AP, S. So be careful of sign, because now we just put the, sorry, I shouldn't use S and P, sorry. Q and R is much better. Q and R. If you put the dagger here, and you have to put the dagger here. Now, what you need to do is you have to first commute the first two here. Therefore, then now you can impose anti-commutation relation on these two guys. The two guys. Therefore, plus and then what you like is this dagger. Okay. And this is a plus sign here. And dagger here. So therefore you have a plus sign. Likewise, one can show the it's the same calculation. So same calculation show that this is if you have a annihilation operator at the minus sign, and which means that if you act the annihilation operator, you get rid of the one particle. Okay, so therefore you lose the energy EP. Okay. On the other hand, if you act the creation operator, you increase the energy EP. That's what it means. Okay. So therefore, so this can be understood as the creation operator of the fermion. Fermions. So therefore, so this can be understood as the creation annihilation operator from this picture too. So therefore, we define a vacuum as the following way. So vacuum. So the vacuum, Fermion vacuum. The vacuum is can be understood as just all the this annihilation operator is just give you 0 if you act on it, and then so you can just have the one particle state as the square root EP AP S acts on. So this is the one particle state. Fermionic state. And the question is, what is the, if you act on BP? So how should we call it? So that's the so question is, so I mean, here one particle states, and here can you call it how to distinguish N and S? Question is how to distinguish. Yeah. Question is how to distinguish it. So what's the difference between A and B? So that's the question. To answer this question, so we just take a look at you have to take a look at the Noether's theorem and symmetry of a Dirac field. So maybe I should call. So at this moment, I should call it A and B. I should call it N. But here, S means the spin, as I mentioned. So S means the spin, and P is momentum, and it has both the same spin and the same same momentum. But there is some quantum number. There is some quantum number that distinguishes these two states. There is some quantum number. That's what we are going to see, and we already knew that why we put the square root to E, right? So to get the square root to E, the reason why we put the square root to E is that here again, I mean P, okay, I call it A, P S cos R is equal to 2EP. Delta RS, and we know that so this E times delta function is Lorentz invariant. Okay. So therefore you have to introduce square root to E, and then also I already erased this square root to this 2 is very nice normalization, as I mentioned last time. So this is one particle state, and then you can just do the same exercise that the n particle states is just so you have n particle states P1, S1, P2, Pn, Sn. It's just you just act on multiple times. P1 is one dagger. Okay, so you can just act multiple creation operator. However, the difference between boson and fermi is that you cannot take Pi and Si. This combination should be different of Pj and Sj. If I is not J. So this is Pauli exclusion principle tells us. Otherwise you get 0. Okay? Otherwise you get 0. If you act the same state, act the same creation operator, you get 0 because of this anti-commutation relation here. Because of anti-commutation relation. So that's the difference. Okay, now so we would like to seek what kind of quantum number distinguish these two, A and B. So that's what we want to see. Which is almost so most of students already knew the answer because you guys just did the homework for scalar theory and then do the Noether theorem in the complex scalar theory. So to distinguish these two, we have to find the quantum number that distinguish them, but that's very super easy because Dirac theory. Do I have the Dirac Lagrangian? Unfortunately, no. So Dirac theory is the transformation. After one student comment about the noise, nobody will stop. Okay, everybody stops talking about. It's so sad now. Anyway, it's a few bit weird. Anyway, so here, this Lagrange is the invariant of the following transformation. The global transformation, so alpha is independent of the x. So there's no x dependence. It's just u1. It's called e to the minus I alpha psi bar x. Okay. So that's easy to see, and this is called u1 transformation. Global. U1 is essentially U1 is Lie group U1. So you know, right? Complex number. I shouldn't say. Okay. Maybe Z in C such that the Z is equal to 1. Okay. So that's U1. It's a group. It's a group. So essentially, that's circle. It's circle. And U1 is just rotation of circle. And then you can easily see this, the action or Lagrange is invariant under this transformation. I mean, even if you multiply e to the I alpha here, if you multiply e to the minus I alpha, they count them. Because I mean, it's independent of x, so therefore the derivative does not see this number. So you can just bring it in. And since we just treat this psi as a complex field, this is totally valid operation. If it is not, if it is real, you cannot do this kind of stuff. Okay. Then, if you have a symmetry, there is a corresponding nether charge. And it's a charge and it's a current. And that's super easy to find. That's super easy to find. How? So let's do the transformation. Let's see. How should I find this current? Sorry, I should be able to. I should be able to do that. Sorry. So this, if you take the infinite transformation, psi of x is psi x and plus I alpha of psi x. But if you treat alpha as very small, it's all fine. Psi bar of x is essentially psi bar of x minus I alpha psi bar x, and this is delta psi, and this is delta psi bar. That's what we're going to do, and so therefore delta s is equal to dq4. First, let's do the formula of psi bar of x I delta psi, and then plus delta psi bar of x I partial bar and psi. Then what we have is that the here. I hope I'm not going to make a mistake. I alpha psi of x. On the other hand, you have minus I alpha psi bar x. Oh, I'm sorry, I'm doing something very stupid. Sorry, let me go back to Nether's term in my note. What I'm doing here? Sorry, I already forgot how to derive this. Nether current is the. Oh, sorry. Now I understand what I have to do. Sorry. So this means this is equal to 0. So therefore, so this is just 0. This is just canonical 0. So therefore, because that's symmetry, so this means that in the node capital J, J mu is equal to 0. And so what we need to do is the so J mu means indeed. I'm very sorry. Phi, delta phi, and plus capital J, right? Plus minus, okay. Minus capital J. Okay, so therefore this capital J mu is equal to 0. So what we need to care about this one. And that's super easy to do. So here is essentially phi, psi, delta psi, and delta psi bar. Okay, so that's super easy to do. So the first term is actually gamma mu, and psi bar. And then delta psi is this guy, so therefore psi is I alpha. And then if you do the integral by parts, you get the minus sign, integral by parts. Do you understand what I meant? So this is gamma mu, partial mu. And if you do the integral by parts, this derivative can act on psi bar, okay? But you have a minus sign. Okay? Therefore, this minus sign cancel with this minus sign here. So therefore, it also have alpha psi bar. I think in canonically you have to put this one into the delta psi here. Gamma mu psi, like this. Okay, so therefore the current J mu is some number. I don't care about number of psi bar, gamma mu, and psi. So this is the current of this symmetry. And then so charge is essentially Q is dq xj0, and which is dq x and psi bar gamma 0 psi. And psi bar is just a psi dagger psi. Okay. So that's the case. Now, so we just plug this Fourier transformation to the integral, and this is Fourier transformation you have to do, and this is indeed equal to dqp. So I'm going to skip today. I'm going to skip all the Fourier transformation part because it's super boring. And minus bp s dagger bps. So that's what we have. We're going to have. So this is the exercise. So you just need to plug in the Fourier transformation where I did. Oh, okay, I already erased. So just plug the Fourier transformation here, and then the integral of the dx integral and dq integral. And then what you get is this one. Okay, I mean, if some of you guys want to know how to do this kind of Fourier transformation, I can perform it on Sunday, office hour if you want to know. But I think I highly recommend you to do this kind of exercise by yourself. So therefore, if you have this necessary Q for your transformation, you have a Q acts on AP dagger zeros. This acts on here, S and is equal to plus AP dagger 0. The same reason as before. Yeah, I mean, you can easily see from the. On the other hand, Q acts on BP S dagger on 0 is minus BP S dagger 0. So here, there's a sign here. There's a sign difference coming from here. So therefore, the plus minus sign difference are up here shown. So therefore, this one particle states you have an opposite. So this opposite charge under this U1 laser current, under this charge. Therefore, this can be understood as electric charge. You see, this Q can be understood electric charge. A has the positive charge and B has negative charge. And then whichever call it in terms of some unit. So therefore, this can be understood. If you treat this one as a fermion, and this is antiparticle. So this is particle. If you treat as this is particle, this is antiparticle, which has, or precisely, so it's with electron, and this is for positron. So electron and positron have the opposite charges. Okay. So therefore, the quantum number that distinguish A and B is this charge is Q. Okay. Necessary charge Q, and this is the electric charges. So and Dirac theory is indeed describe fermion. Fermions, the electron is a fermion. And so if you quantize the Dirac theory, naturally antiparticles show up. So that's one of the reasons why Dirac got the Nobel Prize, because after positron was discovered. So if you quantize the Dirac field, you encounter so-called the antiparticle or positron. Okay. Any question at this moment? Okay. So another way to see how these how they are different is that so you can just consider the spin charges. Spin charges for this states. So as you can easily see, you have to do the Nether theorem again. So Nether charge, so spin charge is Z. I mean, so since the Dirac Lagrangian, so it's Lorentz invariant, okay? So therefore, you can just consider the Lorentz transformation or spatial rotation, and then you can construct the corresponding Nether charges. And then you can just construct the Nether charges. This can be understood as following: side Q, gamma 0. So this is natural charge in fact, this is natural current for the rotation with respect to axis, the third axis. So derivation can be written is written in Peskin's book. Peskin's 61, page 61. I mean, you have to do. Then, if you plug the Fourier transformation, you get the dq, dqp, dqq, 2 pi to the 6. Yeah, I mean, you have to do this kind of computation. E to the minus I q of x. I'm not sure if it is eliminating to write down everything. I'm not sure. Okay, but anyway, so you can take a look at my lecture note. My lecture, I'm not going to write everything. So I'm just. I think it's better not to write everything. I think it's just waste of time. So if you use plug that into here, one can show the following. JZ, I'm going to be very brief from here. Axon 0 is indeed 0 means P is equal to 0. This momentum equal to 0. You just go to frame of reference at the rest frame of this particle. You get the plus minus 1/2 a 0 as stagger 0. On the other hand, if you act B0 state, you get a different sign, minus plus 1/2 B0 as stagger of 0. So you have to do this kind of computation by using Fourier transformation. Essentially, what it means that the here. I mean, plus minus, sorry, I think plus minus means that the plus minus s, s times, and this is minus s times. So s means so s can take plus, s can take a minus, so therefore, yeah, I think, okay, maybe I think, yeah, plus minus, okay. Plus minus is okay. Plus minus and minus plus. So therefore, here, you just treat as the Xi as the 1, 0 is the corresponds to plus 1/2, 0, 1 corresponding to minus 1/2 for electron. On the other hand, on the positron area, 1, 0 corresponding to minus 1/2, minus 1/2. On the other hand, 0, 1 corresponding to plus 1/2. So therefore, depending on positron or electron, so you have to be careful about the sign of the thing. So that's how they behave in the quantum theory, Dirac theory. So therefore, here A and B is the difference between A and B is really this A operator creates electron with P momentum S spin. On the other hand, B created the positron antiparticle with P and spin. And when you consider spin, you have to be careful about the assignment of the really angular momentum or really spin. Any question at this moment? Okay, I think I skipped lots of detailed calculation now. If you want, I can reproduce at Sunday. Otherwise, you should do by yourself. For Fourier transformation. Okay, so now let's finally I'm going to introduce so-called Feynman propagator. Propagator of Dirac theory, Dirac Fermat. So we will do the same thing. So instead of D, I use S for Dirac theory for propagator. So we just consider time ordered 2-point function. Time ordered 2-point function. And then, so we use the psi bar to the Lorentz invariant. So this can be understood as the 0 psi x, psi bar y, 0 if x0 is greater than y0. On the other hand, you have to swap the order of the fermion if it is retarded. And then the cost of exchanging psi and psi bar, you have to exchange psi and psi bar because it's time ordering. Okay? The cost is their fermionic field. Okay? If you swap them together, you have to minus sign. Okay? Because of anti-commutation relation. Okay, so then plug this one into here. Okay, I'll do honest calculation here. So what we get is that the dp, dqp, dqq, 2 pi to the 6, and then so this is what you get. If you just plug into this Fourier transformation to here, you have this one. On the other hand, you have for this forward time, retarded backward time, you have y naught. This is step function I already introduced, and you have B field, B creation rate and annihilation rate. To the plus. Okay. So this is the what you get. So the this part will give you this guy. This part will give you this guy. Okay. And then plug into the computation. So this one will give you delta function. So therefore, what you get is the cube p. 2 pi q 2 p theta function, and we know that the oh yes. So here, as I mentioned, so you have to use this one. So this is homework you have to do. The homework problem as I wrote down. So So therefore, from this anti-commutation relation, we get delta function, and then delta RS will show up. Okay, so you have to sum over spin here. So that will give you this term. Okay. P slash plus M, and then e to d minus I P dot x minus y. So because of delta function here. On the other hand, you have minus sign coming from here, say here, y naught minus x naught, and p slash minus m, and then e to d plus I p x minus y. That's what you get from the calculation. Okay. And do the same thing. Do the same thing for the scalar theory. We just want to write this quantity as the manifestly Lorentz invariant way. Okay, and the first term is, let's focus on first term. So first term is again it's super easy. So we just add again the following contour. dp0 2 pi p square plus m square, minus m square over I. I and e to the I minus I p0 x0 minus y0. So that's the and minus infinity, and that will give you again so this is the contour C. dp0 2 pi p0 minus EP p0 plus EP I and EP minus I p naught x naught minus y naught, and this is equal to, we already know this is 2 EP e to the minus I EP x naught minus y naught. Okay. That's what we already knew. From the analysis, I think it should be correct. So therefore, this 1 over 2 EP e to the minus I EP x naught minus naught can be replaced by this integral. On the other hand, here it's a bit more complicated. So again, so we need to take this is first term for first term. So therefore, first term is indeed dqp 2 pi to the fourth over 2 pi to the fourth theta x naught minus y naught p square minus m square p slash plus m. And I'm not sure if I should put the I here. I think I should put the I here, and the e to the over the minus I p dot x minus 1. That's fine. And then to bring second term, the second term, so we need to put the p again goes to minus p. The spatial one is goes to p goes to minus p, and then let me finish the second term here. So to do that, you have to do the following thing. Second term is equal to dqp 2 pi cube, say y naught minus x naught, 1 over 2 EP, 1 over 2 EP, and then plus p slash plus m e to the minus I p dot x minus y, and you should put p0 equal to minus EP. Do you agree? Do you understand what I'm doing here? Is it okay? So here I put the special one, p goes to minus p. So special one have a minus sign, okay? Special one minus sign. It is minus sign, we cancel this one, minus sign. Then you get a plus sign. But you have to be careful of time component. The zeros component, you have to put the minus sign. This minus sign really comes from really here. Okay? P0, you should put the P0 should be minus EP instead of EP. The same thing here. The plus sign will turn into minus sign for special component. Okay? But for time component, you have to be careful about sign. The time component, the sign issue will be solved by putting P0 equal to minus EP. Okay? So then, you have to do the same trick. I forgot how to do that. So second term, you have to take this contour EP and plus EP, and then what you end up with is the the same thing. So this is C2 and C1. C1. So then, so here again, you need to do the same thing. P0 minus EP, P0 plus EP, and I and E to the minus IP0, x0 minus y naught. Okay. So then, what you end up with the really you can pick a pole from minus EP. That will give you the P0 minus EP condition. Okay. On the other hand, here you have a EP condition. Without so this one is essentially we need to put the P0 equal to EP at this moment. But after swapping this one, you just change the sign here. And that will give you 1 over 2 EP e to the minus I P0 minus x0 minus y0, but the P0 is equal to minus EP. So combine them together, so what you end up with the I times SF x minus y is in, sorry, no I, sorry. Is d 4p 2 pi p slash plus m times I times p square minus m square, and the contour is again the same as before. This one, or you can just use epsilon prescription to specify the pole, and e to the minus I p dot x minus y. So that's the final propagator of the Dirac theory. So therefore, so it's very important to put the here minus sign here. Otherwise, you don't get the minus sign. And then swapping, I mean, this Fermat binomial go to p slash minus n. But if you change the sign of the spatial momentum and be careful about the contour, then you can bring everything manifestly Lorentz invariant way like this way. Okay, so it's a very beautiful form, and then what we need to do is just check the sum of the stuff. So since we know, so in momentum space, so this people just write like this way. Later I will explain what it means. And this is equal to p slash plus m. So this is in momentum space, propagator is like this way. And since we know Dirac equation is square root of Craig model equation, this is indeed equal to I p slash minus m. And as you can easily see, so this is a green function of the again Dirac equation. Okay, so the Dirac equation is something like I slash m, and then SF of if you act SF of x minus y. Okay, so then if you act this one into here, what you create is that this will create a p slash minus m. P slash minus m. Okay, can you see that? So derivative acts on p, so therefore I times minus I is plus, so therefore p slash m. And if you multiply them together, numerator and denominator cancel. And then what's left is dp integral times e to the minus ipx. Therefore, that will give you the delta function. Okay. So therefore, the final propagator is indeed equal to is the same analogous to the scalar theory, the green function of the equation of motion. Okay. Any question at this moment? Okay, so we finish at least the basic part of free Dirac theory, and then we will move on to the now gauge theory, abelian gauge theory, or Maxwell theory, quantized Maxwell theory next time after watching. By the way, do you need office hour this Sunday? Will you be around? But yeah, I think we can connect at least Zoom. I may not be in office. Maybe I'm in office. Maybe I'm in office. I most likely I'm in office. But if you have a question, you can ask from home or your hometown or whatever from Zoom.